Welcome to this presentation on adaptive autoscaling policies via AI in Kubernetes, predictive versus reactive models. We'll explore topics such as understanding reactive autoscaling, the promise of predictive autoscaling, key components of predictive autoscaling, comparing reactive and predictive approaches, deep dive into time series forecasting, implementing predictive autoscaling, steps, challenges in predictive autoscaling, tools and libraries for implementation, and conclusion and next steps. Reactive autoscaling relies on predefined target metrics, such as maintaining CPU utilization around 70%. When usage exceeds this threshold, the horizontal pod autoscaler, or HPA, triggers scaling up. However, this approach is not without challenges. Latency spikes can occur due to sudden demand, leading to a thrashing effect during fluctuating traffic. Furthermore, over-provisioning resources can result in unnecessary costs. Understanding these dynamics sets the stage for exploring more advanced predictive models. Predictive autoscaling empowers us to anticipate traffic surges before they occur, allowing for preemptive scaling. By leveraging historical data, we can enhance our predictions significantly. Algorithms like ARIMA and LSTM refine our scaling strategies, ensuring smoother performance. Ultimately, this leads to an enhanced user experience, making our applications more resilient and responsive. Data collection is crucial, focusing on metrics like CPU, memory, and custom KPIs. We utilize forecasting models that incorporate time series and deep learning techniques to predict future resource demands. A robust prediction API acts as a microservice endpoint, delivering forecasts effectively. Finally, integrating external metrics allows the horizontal pod autoscaler to leverage these predicted values for optimal scaling decisions. Reactive scaling responds to current metrics but suffers from latency delays. It features a simpler configuration and broader documentation availability. In contrast, predictive scaling uses future forecasts to anticipate demand changes, but it comes with a more complex setup and limited documentation resources. Each approach has its strengths and weaknesses that can significantly impact performance in dynamic environments. Understanding time series forecasting is crucial for adaptive autoscaling. Classical methods like ARIMA and Holt-Winters excel in managing seasonality, while probabilistic models like Gaussian processes effectively capture uncertainties in data. Deep learning techniques, specifically LSTM and GRU, allow us to model intricate dependencies over time. Lastly, reinforcement learning enhances our approach by optimizing scaling decisions based on performance rewards, ensuring efficient resource utilization. Choosing the right forecasting model is crucial. It should align with your team's expertise. Collect at least 14 days of historical metrics to ensure accuracy. Next, build an inference service that processes these metrics to provide reliable predictions. Finally, integrate a custom metrics adapter to connect your predictions with the horizontal pod autoscaler, enabling seamless autoscaling based on forecasted needs. Limited real-world case studies exist that compare predictive with reactive autoscaling methods. This lack of comparison makes it difficult to assess their effectiveness. Additionally, there are few standardized benchmarks for performance metrics, leading to inconsistencies. While community projects offer valuable resources, documentation often falls short. Therefore, continuous monitoring and iteration are essential to refine and improve predictive autoscaling strategies effectively. CADA enables event-driven autoscaling, ensuring resources align with demand. The Prometheus adapter integrates custom metrics for tailored performance insights. Kubeflow serving facilitates the deployment of machine learning models, enhancing application intelligence. Lastly, open-source options allow for flexible inference services, supporting diverse use cases. These tools create a robust ecosystem for adaptive autoscaling in Kubernetes. Transitioning to predictive autoscaling significantly enhances responsiveness in Kubernetes. Start by analyzing historical data and experimenting with various forecasting models. Sharing your findings with the community helps build a valuable knowledge base. Always remain curious and adaptable as scaling strategies evolve.